Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. We have three matrices, A, M cross N, B, N cross P, and C, P cross Q, and we want to decide which parenthesization, ABC or ABC, is faster by comparing operation counts. Then apply the same idea to vector expressions, and finally derive the general inequality that tells us exactly when ABC is faster. Matrix multiplication is associative, so both parenthesizations give the same final M, Q matrix. But the intermediate matrix sizes change, and that changes the operation count. If we create a large intermediate matrix, we pay for it twice, once to build it, and again to multiply it. Let's plug in the specific sizes and compare total multiplication counts. Both orders are legal because the inner dimensions match, 4 with 4 and 7 with 7. First, multiply A and B, producing a 2 times 7 intermediate. Multiplying a 2 by 4 by a 4 by 7 requires 2 plus 4 plus 7 scalar multiplications. Now multiply the 2 times 7 intermediate by C to get the final 2 times 10 result. So ABC takes 196 multiplications total. Now try the other order. Multiply B and C first, producing a 4 by 10 intermediate. This intermediate is bigger, and it already costs 280 multiplications to build. Then multiply A by that 4 times 10 intermediate to get the same 2 times 10 final matrix. Total cost is 360 multiplications. Now we compare totals directly. The winner is ABC because it avoids forming the larger 4 by 10 intermediate matrix. Vectors can be treated as thin matrices. That lets us use the same dimension and intermediate size thinking. Both produce a 1 times n row vector in the end, but the intermediate object differs dramatically. First, compute the dot product U times V, just a single scalar. A dot product costs n multiplications, then scaling WT by that scalar costs another n. This order creates a full n times n matrix as the intermediate, much larger than a scalar. Building VWT costs n squared multiplications, and multiplying UT by that matrix costs another n squared. So the clear choice is to do the dot product first, then scale. Avoid forming the big n times n outer product. Now we want a general condition based only on MNPQ for when ABC is faster. We start by writing faster as has smaller multiplication count. Dividing by the product MNPQ turns each term into a clean reciprocal of the missing dimension. After simplification, we get a simple inequality comparing sums of reciprocals. Parentheses don't change the final matrix, but they change what you build in the middle, and that controls the work. In the numeric example, forming the smaller 2 times 7 intermediate wins. For vectors, compute a scalar first, not a whole n times n matrix. This inequality is a quick test. It tells you which parenthesization is cheaper before you compute anything. Keep the momentum going. Click into the next video, and you'll learn how to extend this same idea to long chains of matrices, so you can choose the fastest multiplication order like a pro.